Hello. In this video, we're going to talk about the fundamental theorem of calculus. It actually has two parts to it, and in the past we explored the fundamental theorem of calculus as it relates to finding areas under the curve. So for example, we would say if this was the function f of x, then the fundamental theorem of calculus says if you want to find the area under f of x from point A to point B, you just take the antiderivative of f of x and evaluate it at B, and you take the antiderivative of with respect to x and you evaluate it at A, and when you subtract those two, that produces the area. So that's the way that we use the fundamental theorem of calculus in the past. It actually goes in a reverse way as well, and it's subtle, and in some cases it feels kind of obvious, but really it's just a simple kind of a concept. Essentially, if you want to get what the other form of the fundamental theorem of calculus is, in its basic essence is if you take a function and integrate it, you get a new function. If you take its derivative, you get back where you started. It seems like so simple, it's obvious, but you have to understand historically that was not an obvious concept and it needed to be proven. So anyway, let's see how it works in practice and try to understand the language behind the concept. In other words, how do we communicate the fundamental theorem of calculus so we understand it better? The first notion is to understand that there's a new way of defining a function. And in this case, what we're going to do is, first of all, understand that we're going to define the x-axis as a t-axis. We could say time, for example. It could be anything. And then the y-axis is just the y-axis. Then I want to create a function that tells me what the area under the curve is from A to any random variable x. So I can actually choose x to be any number, and whatever I choose x to be, it's obviously going to change the area. So area is a function of how large this interval is. If we make the interval larger, we're going to have more area, and so on. So here's how we can define a of x. Usually when we find a of x, we put a of x equals, and then over here is just going to be a straight up function equation. In this case, it would just be something like something x squared. But instead of defining the function as just a relationship to x's, we could define the function the way area functions are defined. From the fundamental theorem of calculus, we learned that the area is actually the integral from a to x of f of t dt. So again, what I've done is I've just created a new way of defining functions. Instead of defining functions the traditional way, we'll define the functions where the independent variable is the upper bound of a different function, of a different variable, so to speak. So, in other words, the a of x function is just this cubic polynomial, which is little more than the antiderivative of f of t. But this is the x-axis and this is the y-axis. Anyway, so I can now figure out then that if I take the derivative of the a of x function, so this is a of x, which is a cubic polynomial, if I took its derivative, this is going to be a prime of x, which is f of x, which is where I started from. So basically, we took this function as a function of time. We turned it into a function of x by saying I'm going to make variable the upper bound of my area function. By making the upper bound of the area function variable, then we can translate that the derivative of the integral is the function we started with. Again, it's kind of confusing. It's harder to explain than it is to just see and just to visualize. But if you want to look at it this way, looking at this picture up here, the pink shaded area, or salmon colored, that area function is represented by this curve right here. So once again, oh sorry, let me finish up this concept first. Sorry, I jumped ahead of myself, so we'll get back to what I was trying to say earlier. Let's look at the mathematics and the language a little bit more detail. In the previous slide, what I said was apparently if I take a of x and define it as the integral from a to x of f of t dt, that the derivative of a of x is just f of x. That's basically what we just sort of discovered. Try to unpack that a little bit is what I'm trying to do here. So let's go back and just look at the integrals. If we just integrated from a to x, f of t dt, then according to the first part of the fundamental theorem of calculus, we get big F, the antiderivative of f of x, subtract the antiderivative of f of a. Now remember, what we're asked to do is to take the derivative with respect to x of the integral shown here. The derivative with respect to x of big F of x is, well, back to f of x again. The derivative of f of a, on the other hand, remember this is the derivative with respect to x of a function at a, which is a constant value. Remember, we fixed the left-hand bound. The derivative of a constant is 0. So here again, we've actually got the derivative, the integral of a function is the function where the x substituted in, so it's kind of like a shortcut or something like that. So this is, again, what we're saying. Try to highlight that for you using these graphs up here. First of all, I start with a function. It's a linear function, and then I create a new function which will tell me the area under this curve as a function of where I put my slider along the x-axis. So x variable represents how wide this interval is. Depending on the size of x, it's going to create a different area. So for example, if x was the same as a, then the area would be 0. So that's right here. Boosh. If we go backwards, we're going to get negative areas, so that's what's going on here, and so on and so on. Anyway, now that we get this, we've just created a new area function, whoosh. If we were to study the slope, that is the rate of change of this new area function, well, I get a brand new function of x, which is exactly the same as the original function that I started with. So here again, we can see that this is a function of time, but because of our fundamental theorem of calculus, we've got the same function, but now it's dependent on x, specifically where I choose x to be. So again, it just kind of seems a little weird, and it seems kind of like, well, that's it. But let me show you these examples, and it might drive home a little bit more clearly what's going on. First of all, just again, we look at this applet. This is a pretty cool applet, by the way. You can slide this along, and it's going to show you the area, and then it gives you the net area over here. It all calculates it out for you. This does look like a cosine function. In fact, it looks like y equals 2 times the cosine of x. But instead of defining it as f of x equals 2 cosine of x, it's defining it as f of x equals the area from 0 to x of this f of t function. So let me show you, first of all, if I let x equal this number right here, which I'm going to assume is pi over 2, then the area under the curve is 2. So in other words, if I choose x to go along this far along the x-axis, then 2 represents the area under that curve. If I were to continue to let x go all the way over to here, which is like pi, then this area and this area, they're going to subtract out and leave us with 0. So I put a point at pi 0 right there. If I continued this pattern, I would actually be able to see that depending on where I choose x to be, the area under the curve is first going to go up and it's going to max out at 2, but then we're going to start having negative areas, and so we're going to go back down to 0, and then we're going to have increasingly more negative areas, so we go down this way, and so on. So what I end up with is the antiderivative of the function that was given is actually f of x, which we can define as 2 times the sine of x. So going back down over here, if I was to take the derivative of f of x, it's the derivative of 2 times the sine of x, which is 2 times the cosine of x, which was the function that I started with. So once again, we can see the same truth being said over and over again. We start with the fact that we define our function as an area function, and then when we take its derivative, we're just back to the original function in terms of x. So here, I don't really know what the integral of e to the x squared is, or e to the t squared for that matter. I don't know how to integrate that right now, so what I'm going to do instead is just say, look, there's a way to integrate it. In other words, if I took the derivative of some function, I'm going to get back to e to the t squared. So I'm acknowledging the existence of the integral without actually defining it explicitly. Now though, when we go from 0 to x of our function, consider the fact that this integral, definite integral, can be evaluated by the antiderivative x minus the antiderivative of 0. Thus, the derivative is going to be the derivative of f of x minus f of 0. Now, the derivative of f of x we've defined as e to the x squared. And the derivative of f of 0, well, it doesn't really matter what f of 0 is. It's constant, and the derivative with respect to x of that constant value is 0. So here again we say e to the x squared. Now stop, I put a shortcut there because what I wanted you guys to see is if I say the derivative with respect to x from 0 to x of e to the something squared d something, then we just replace the formula with x. And a lot of people are going to shortcut their thinking and just say that's all you got to do. Things get a little funky though right here because you'll notice now my boundaries have changed. Instead of going from a constant to our variable x, we're going from x to our variable, or to our constant. So, to understand what to do here, the first thing I recognize is the way we define the fundamental theorem of calculus, we have a fixed left-hand bound, and then we head off in the right direction and allow x to be defined as anything to the right of our left bound. In this case, what we're doing is we're starting with a fixed value, let's say 3 for example, and we're going to head in the opposite direction. Boosh. Now if we do that, that's fine, but the problem is we are reversing the order of the integration process, and therefore we're going to get the opposite. Because we went in the opposite direction, we're going to have an opposite value representing this area. Easy fix. If we're going in the opposite direction, all we have to do is take the opposite of our derivative by just changing the boundaries. So right here, for example, you can see we went from x to 3. I just made it the opposite of the derivative from 3 to x. Now we do what we did in the previous example, replace t with x. Don't forget to move down the negative that came from switching around the boundaries, and we're good to go. Here again, nice and simple. What they're trying to demonstrate here, though, is you don't have to be bound by x. This is an integral with respect to x, but we're going to differentiate with respect to time. So the purpose of these exercises are to say, pay attention to your variables because some are variables and some are constants, and this is going to tell you the variable is t, and so going to tell you then that x is a constant. So this is using the fundamental theorem of calculus. Over here, once again, the variable is b instead of x, so here's what our result is. So here what we have is a virtual generalization. If we're differentiating with respect to x from a to x, a function, then we just get f of x. If we're differentiating with respect to b from a to b of a function, we get f of b. So pretty straightforward stuff. Next example, and I just have a couple more here. The next example just deals with what happens as we go from a to b of f of x dx, and then I take the derivative of it. Keep in mind that we're going x to x, and therefore, sorry, I lost my train of thought here. I'm sorry, that's what we're doing here. Yep, this is the derivative with respect to x. But when I look at my integrand, it's going from a to b. Both a and b are fixed constants, not variables. So if I just look at the integral itself, when I integrate f of x from a to b, I get big F, antiderivative f of b, subtract f of a, which is a fixed constant. So when I take the derivative with respect to x of that fixed constant, I'm going to get 0. So that's why you can't just like say, all right, this is dx, I'm just going to take whatever I see inside the parentheses and just put an x where I see a t. Don't do that. Pay attention to your boundaries before you start jumping around doing crazy stuff. Here, the problem is slightly different. This time we're differentiating with respect to x, the function f of x, and then we're going to integrate that from a to b. So first of all, the derivative of f of x is f prime of x, and then the fundamental theorem of calculus says that the integral of f prime of x is just f of x again. We're going to go from the boundaries from a to b. Therefore, the expression shown here is actually equivalent to f of b minus f of a, whatever f of x was. Here, notice the operation for derivative is happening inside and outside the integral. So here we have to pay attention to the variables. First, we differentiate with respect to t, natural log of t, and when we do that, we're going to get 1 over t dt. Now we go into phase 2, and we apply the fundamental theorem of calculus here, and we go from a to x, differentiate with respect to x, so that's where we just do that substitution piece. Over here, we have the derivative with respect to t of f of t, which is the derivative, well, basically this is a generalization of what we said over here. Notice that in this case we had the derivative of the natural log, which is 1 over t, and then we substitute in for x, we get 1 over x here. The derivative of f of x is f prime of x, and then we do the substitution. Finally, this gets a little bit closer to what IB is going to do. They're going to expect that you understand the nature of the fundamental theorem of calculus, so they could ask you a question here. Differentiate. Now what you'll notice is the boundaries go from x to x squared, and remember we're differentiating with respect to x. But this is not x, this is the square of x, so it's slightly different. So how do I handle it? Well, the first thing I'm going to do is go back to my original fundamental theorem of calculus and just integrate this, which I can't do because I don't know how to integrate the sine of t squared at the moment. But I'm just going to call it f, big F, of t. Then we're going to have x to x squared, so basically I'm asking for the derivative with respect to x of f of x squared minus f of x itself. Now, take the derivative of a difference is equal to the difference of the derivatives, just to micromanage a little bit. And the second derivative that I see there is pretty straightforward. That is, the derivative of big F of x is sine of x squared. I knew that because of this in the fundamental theorem of calculus and all that stuff we did in the previous slides. Over here it's a little bit different though, because if I take the derivative of f of x squared, I got to remember the chain rule. So it's going to be f prime of x squared times the derivative of x squared itself. So that's where the chain rule comes into play. And I'm going to take this then, derivative of x squared is 2x. Notice that f prime of x squared is the sine of x squared squared. Just as f prime of x is the sine of x squared, f prime of x squared would be the sine of the square of x squared. So anyway, finishing up there, I've got a little cosmetics. X squared squared is x to the fourth, and the 2x I bring over in front so it doesn't get lost. And there you go. So this is a little bit different than just wherever I see a t, I replace it with x. We have to remember there's some chain rulage going on here. So I hope you find that helpful. I'm sorry if it was a little overlong, but again, it's really more about understanding a very, very simple looking concept. It's deceptively simple though. Well, thanks for watching. Have a good day.